Hello everybody, and welcome to a new entry in our 2020 tutorial video series. My name is Robert Rüger, and today I want to talk a bit about the upcoming 2020 release of the Amsterdam Modeling Suite. I especially want to talk about how the complete integration of ADF into the AMS driver can help speed up your DFT calculations. If you have used other codes such as BAND, DFTB and ReXFF in the previous release, you might already be familiar with the AMS driver setup. For everyone else, I have a quick summary right here. Basically, the AMS driver and its engines technically separate calculating energy and gradients from using them. Calculating energies and gradients given a system geometry is the responsibility of the engines, while the AMS driver takes care of all changes in the geometry. One could say that the AMS driver explores the potential energy surface and steers the engines across it. What we now call engines, for example BAND, DFTB and ReXFF, used to be separate programs that users would run, each with their own input and output files. Now the engines are technically just libraries that are used by the AMS driver under the hood, while the user only interacts with the AMS driver. This setup has the advantage that all new applications added to the AMS driver are immediately available for all supported engines. The AMS driver already has many methods to explore a potential energy surface, and more are added with every release. Furthermore, we can very easily exploit parallelism at the driver level, say for a numerical calculation of a derivative, by running multiple instances of an engine in parallel. In the 2019 release of the Amsterdam Modeling Suite, our flagship DFT code ADF has not yet been integrated into the AMS driver and still exists as a standalone program. This was just because ADF is our biggest and most complicated code, and as such was the most effort to integrate into the AMS driver. With the 2020 release of the Amsterdam Modeling Suite, the integration of ADF into the AMS driver is finally complete. This means that in the upcoming release, ADF no longer exists as a standalone program, and users will instead use ADF through the AMS driver. People using the graphical user interface should barely notice this change, but users writing their own input files by hand will need to be aware of this and slightly change their inputs. Don't worry though. The AMS driver input is not too different from standalone ADF's input, and we will provide a script that can help you convert your existing input files. There is also a bit of renaming going on in the next release. Traditionally, the prefix ADF was used to refer to the entire suite of programs. For example, our GUI program for setting up jobs was called ADF input, even though it would also be used to set up DFTB and ReXFF jobs. Starting with the 2020 release of the Amsterdam Modeling Suite, we will only use ADF to refer to our flagship molecular DFT engine, while AMS is used for all general functionality that is useful no matter what engine you're using. So what advantages does it have to have ADF integrated into the AMS driver? First of all, there are a couple of potential energy surface exploring applications in the AMS driver that we did not yet have in the standalone ADF. For example, the multi-coordinate PES scans, nudged elastic band, and molecular dynamics. There is also the neat little feature of a Passpoint characterization, which I want to talk about in more detail later. All these features will of course become available for ADF now. Furthermore, integration into the AMS driver also allows for the driver-level parallelization of certain jobs. As an example, consider the calculation of a Hessian in an electronically excited state. This used to be a very expensive job, since the Hessian has to be calculated numerically in an excited state, and every displacement requires a TD-DFT calculation. It is still an expensive job, but by parallelizing over the displacements at the driver level, we can easily make this job scale to hundreds or even thousands of CPU cores. Finally, the integration of ADF into the AMS driver gives us the possibility to combine ADF and other engines within one and the same job. I want to show you an example of this now. We are going to do a part of a new tutorial that will be in the documentation of the 2020 release. So once the release is out, you can look up the tutorial and then try my tips and tricks out for yourself. In this tutorial, we will look at the insertion step of ethylene polymerization catalyzed by a homogeneous Ziegler-Natta catalyst. We're going to do two steps from the tutorial. An initial linear transit calculation to find a candidate structure for the transition state, and then starting from this structure, we're going to run a real transition state search and verify that we have indeed found a transition state. In the tutorial, the first thing that you will learn how to do is how to build and optimize the structure. However, I've already done that, so I can just load it from an XYZ file. This is the structure. Now let me configure the engine ADF. We're going to use GGA with a D4 dispersion correction as the exchange correlation functional. I'm going to increase the quality of the basis set to DZP. And we're going to use relativity scalar. I don't actually have to set this now in AMS2020 because relativity scalar is the new default. I also have to set a total charge of 1 because this compound is charged. Next I want to configure the solvation. So I'm going to go to the solvation panel, select Cosmo as the method, and select toluene as the solvent. This defines the potential energy surface. Now we have to say what we're going to do on this potential energy surface. I want to do a linear transit calculation where I pull this carbon towards this carbon and this carbon towards the zirconium in the center. Let me set this up. I'm going to select PESScan. A PESScan is just a multi-dimensional equivalent of a linear transit calculation, but since we only have one scan coordinate here, we might as well call it a linear transit. Let me set up what I just said. We're going to pull this carbon towards this one, and I want a final distance of 1.5 angstrom. I also want to pull this carbon towards the central zirconium. And here I'm going to use a final distance of 2.3 angstrom. That should be roughly a reasonable distance between a zirconium and a carbon in a methyl group. Basically like the one we have here. Here our distance is 2.27. Now I have these set up as two distinct scan coordinates. That's not what I want. I just want them to change together as one concerted coordinate. So I'm going to move the second one into the first scan coordinate, and now I have only one. And I'm going to increase the number of points here to 20, just so that we get a bit smoother movie. I'm also going to go to the convergence details panel here and relax my convergence criteria by a factor of 5. For a linear transit where we don't need to converge every point that deeply. It's enough to get something reasonably good. After all, we only want to use the highest point of the linear transit as the input for our transition state search. Right, let me relax it by a factor of 5. Okay. Now this is where I want to show you the first trick. Now what is a linear transit calculation? It's just a series of independent geometry optimizations in which a constraint is changed from one spot to the next. And as for any geometry optimization, we can speed it up by having a better initial Hessian. After all, we're using a quasi-Newton optimizer. It's set to auto here by default, but I now want to set it to calculate with a fast engine. Now what is a fast engine now in this case? We're using ADF as our main engine, so our basic level of theory is DFT. Calculate with a fast engine basically just means to use a lower level of theory for the initial Hessian and then properly calculate the Hessian using an engine at this level of theory. For ADF, calculate with a fast engine means to calculate the initial Hessian at the DFTB level of theory, specifically with the GFN1 XTB Hamiltonian, since that one is available for all elements of the periodic table. We're going to select this now, and then I'm going to run the job. Okay, it is a bit later now and our job has finished calculating. We found this energy profile here along the linear transit, and let's have a quick look at the movie. This looks pretty good. Exactly what we expected, and I think we should have found a good candidate for a transition state right here. Now let's see how much the DFTB initial hashing actually saved us in terms of total number of steps in these geometry optimizations. To do this, we can go here to View and untick Accepted Geometries Only. Then we get to see the entire trajectory, not only the converged frames of the linear transit. As we can see, in total it took 163 frames for the entire linear transit calculation to complete. Now, in order to compare that with the default choice of the initial hashing, I ran the exact same job, but then selecting the default instead of calculating the initial hashing with the faster engine. This is the result. In terms of energy profile, we can see that it's basically identical. So as expected, the XTB initial hashing did not really have an influence on our results exactly as we wanted. But in terms of number of steps that it took, let's have a look here. Untick Accepted Geometries Only. And there we see that this one took 261 steps. So we saved about 100 steps. That's pretty good, I would say. Okay, let us now move on to the actual transition state search. For this, we're going to pick the highest point from our linear transit trajectory and export it as an XYZ file. Let's call it TS candidate. Now we will make a new input where we can import the geometry we just exported. There it is. Let me make the window a bit bigger. Now I'm going to have to set up things in the same way as I did for the PESCAN. So we need a total charge of 1. I'm going to use PBED4 and a DZP basis set. And I also have to set up the solvation method as Cosmo with a toluene solvent. All right. Then I'm going to select transition state search as the task and click through here to the details panel. And here I can select the initial hashing. Now for a transition state search, it's quite important to have a good initial hashing because it can actually determine the success or failure of your entire job. In the past, we often recommended to choose calculate here, which will just calculate the entire hashing at the actual level of theory. So it will calculate the full hashing with the DFT here. Now we're going to use calculate with a fast engine, just like we did for the PESCAN, which will calculate the initial hashing at a DFTB level of theory with a GFN1 XTB model Hamiltonian. Also, I want to click characterize Passpoint yes here. This enables the Passpoint characterization in the AMS driver I mentioned earlier. Now, what is this Passpoint characterization? We call it a Passpoint characterization when, given a system's geometry, we determine if the corresponding point on the potential energy surface is a non-stationary point where the gradients are just too large, a local minimum with no imaginary frequencies, a transition state with exactly one imaginary frequency, or a higher order saddle point with more than one imaginary frequency. This is really the information that we need at the end of a transition state search. After all, we're not really interested in the full hashing and the system's normal modes of vibration, but just in the number of imaginary frequencies. The AMS driver allows to determine the character of a Passpoint without calculating the full hashing. In order to do this, we calculate just a few lowest frequency normal modes through an iterative diagonalization of the hashing matrix using a Davidson class algorithm. It is easy to understand how this works if you realize that a multiplication of the hashing matrix with a trial nuclear displacement delta can be approximated as a numerical derivative of the gradient vector along this displacement. It is therefore possible to perform the multiplication with the hashing matrix without actually calculating it. This allows us to use iterative diagonalization algorithms like the Davidson algorithm, for which a matrix vector multiplication is enough. Normally, these algorithms are used to calculate eigenvectors of huge matrices that are too large to store in memory. This isn't the case here. The hashing matrix is small. We would just like to avoid calculating it because doing so would be very expensive. The great thing about the Passpoint characterization is that on average it converges after about 15 iterations, or 30 nuclear displacements for a two-sided derivative, irrespective of the system's size. For systems beyond roughly 25 atoms, this makes the iterative Passpoint characterization much faster than the direct calculation of the full Hessian. Alright, now that the Passpoint characterization is enabled, I can just save and run my job. Let's call it TS search. Okay, the job is running. I will leave it running for a bit and then get back to you when I have some results. Alright, our job has finished, and if we look at the very end of the log file, it says here Passpoint character geometry corresponds to a transition state. So we did find a transition state, and if we go to ADF spectra, we can see its geometry, and we can also see the two modes that our iterative diagonalization of the Hessian produced. This is the mode that goes across the saddle of the transition state, and this is the second lowest, mostly corresponding to a rotation of these weakly bound rings here. For comparison, I also ran the exact same job, but not using the iterative Passpoint characterization in the end, but instead calculating the full Hessian. The results of which we can see here. The geometry is identical, and also the two lowest modes are basically identical. Let us now have a look at some timings. In the left column you can see the timings for the reference calculation, in which we calculated the full Hessian twice. Once in the beginning of the job as the initial Hessian to start off the transition state search with, and once in the end in order to verify that we have indeed found ATS. In the right column we have calculated the initial Hessian at the DFTB level and performed the iterative Passpoint characterization in the end. As you can see, the initial Hessian at the DFTB level cost us no time at all. It was of course a bit less accurate than the DFT calculated Hessian on the left, but we did still find the transition state, and the TS search only took 5 steps more, which isn't much of a difference. For this particular job, the iterative Passpoint characterization was not faster than a full calculation of the entire Hessian. This is because for GGA functionals, ADF can calculate the Hessian analytically, which is quite fast. Furthermore, with just 31 atoms, the system is still rather small. The analytic Hessian in ADF is not yet supported in combination with all exchange correlation functionals. If I redo the exact same calculation, but switch to an exchange correlation functional for which the analytic Hessian is not available, the iterative Passpoint characterization is easily faster than the calculation of the full Hessian. This concludes this week's tutorial video. We hope you found these tips and tricks useful. If you have any questions, just leave them in the comments below and we will get in touch with you as soon as possible.